Hello everyone and welcome to another episode of Automation with Atmega32 series of video tutorial, and today we'll be looking at the general layout of Atmega32 chip in terms of its pinouts. And actually what you are looking at on your screen right now is Atmega32 chip, and you can also see how its pins are set up. And let me just go to let me take you to if you look at it very well, just on top of it we have a notch. If you're keen enough, you'll be able to see a notch, and then just beside the notch we have a dot sort of, and these knots and these dots right beside PB0 is always there to help us identify the last and the first pin. Like if we have it like this, PB0 is always going to be our first pin, and PA0 is always going to be our last pin. And in total we have Atmega32 chip actually has 40 pins, and PB0 is the first pin, pin number 1, and PB6 bottom left is bottommost left pin is our pin number 20. Then PD7 is pin number 21, and then PA0 is the last pin, pin number 40. And then you'll be able to notice then that Atmega32 chip has 40 pins in total, out of which we have 32 GPIO pins. GPIO simply mean general purpose input output pins, and general purpose input output pins of which Atmega32 has 32 of them are those pins that we get to connect whatever we need to control using Atmega32. We have input devices like switches and sensors. We can directly connect them to our microcontroller using these GPIO pins, and we have also output devices like LCD, 7-segment displays. We have LEDs. We have buzzers. We have a number of we have wireless devices that we can connect through a microcontroller using GPIO pins. And those are the key functions of GPIO pins. And now let's just go to the function of these pins, both as GPIO pins and other functions that can always be allocated to these pins. And before getting into the nuts and bolts of it, I would want for everyone to understand that Atmega32 is built in terms of ports and pins, and Atmega32 has 4 ports, of which every single port has 8 pins, 8 GPIO pins. That makes it 32 GPIO pins because it has 8 ports. Let's consider port B, which has pins PB0 all the way to PB7, or rather pin B0 all the way to pin B7. That's on port B. Then we have port A, pin A0 all the way to pin A7. That makes it 8 pins. It's confusing because each port has the last pin as pin B7, PA7. You might think there are 7 pins, but we are indexing from 0, so it's 0, 1, 2 all the way to 7. That makes it 8 pins and not 7. And now just to describe each pin with its sum of the pins, I'm going to describe their functions in terms of being GPIO and other functions. If we look, let me just go to pin B5, pin B6, and pin B7. MOSI or master out slave in MISO, master in, slave out, and SCK. These are always used for SPI communication. And it's also important to note that it is through SPI communication that we are going to download our code or burn our code into microcontroller, SPI communication. Then we have reset pin right below pin B7. This is always used to reset the microcontroller. We have VCC and GND. VCC always goes to 5 volts, and GND we connect it to 0 volts. These are used for powering Atmega32 chip or any other microcontroller, and they are always explicitly described or labeled. It's a common standard among all microprocessors and microcontrollers. Wherever you see VCC, like Atmel family of microcontroller mostly use 5 volts only on their VCC. We have some other microcontrollers like STM32 microcontrollers. They mostly use 3.3 and volts. So we have 5 volt microcontrollers and microprocessors. On the other hand, we have 3.3 volts microcontroller. So it's another area that we always have to look into before we, in terms of setting up the power supply for a microcontroller. Just right below, we have XTL to XTL1, XTAL to XTAL1. These are normally used when we are using external oscillator. Actually, by default, Atmega32 has an internal oscillator which always run at a speed of 1 megahertz. But for the sake of we have there is always going to be a time when a 1 megahertz frequency or the internal oscillator itself does not might not be switchable for some operation, like when I was implementing UART communication and I2C communication. I noticed that it was never going to work with the internal oscillator, so I had to switch to external oscillator, 16 megahertz, so to speak. So and these two pins are always going to be used to connect external oscillator, and we'll see that how it's done and how to set fuses for Atmega32 chip to run on external oscillator of frequencies above 1 megahertz for a sensitive communication and like I2C communication, SPI, and UART communication. UART communication is whereby you connect other serial devices like GSM modules, which like when we are connecting our microcontroller and we need it to communicate to our PC, the best way to do it is through UART communication, which always involve transmission of data in serial format. So we'll do UART communication and we'll see how to set up registers for inside the Atmega32 chip. And the concept of UART communication is very important in the field of automation because there are a lot of communication between our chip and some other peripheral devices. And now right below our XCL1 is pin D0, this one is port D now, and the first pin D0, is we have RxD, and this is a receiver pin, and TXD, which is always transmitter pin, and these are always used in UART communication, like I've said before. And when we have a UART device, the TXD pin is always going to be connected to the RxD pin of the UART device and vice versa. So like I said just a while ago, UART communication is very important and key in terms of trying to get into automation. So we'll do UART communication. And now right below it we have pin D2 and pin D3, INT0, INT1. These are used for setting up external interrupts, like when you want to connect, when you want to achieve interrupt using a switch, you can do it through pin D2 or pin D3. So fortunately for us, Atmega32 has two pins where we can achieve that external interrupts. We're going to do external interrupts and we'll see how it works using buttons. And now it's also an interesting part of automation. Then right below we have OC1B and OC1A. These are always used with waveform generation mode to generate PWM. PWM is a very important concept in terms of communicating and generating signals that you can use to generate audio signals. We also have servo motors that we can only interface to with a microcontroller using PWM, and we are also going to do PWM, and we can only achieve them using these two pins, OC1B and OC1A. We are going to see how to set our registers to give us a waveform generation modes that in turns will give us the desired PWM signals for desired functions that we might intend to use. And now, like when you're going to control the speed of a DC motor, we use PWM. PWM simply means pulse width modulation, and these two pins will help us generate such PWM signals. And I'm going to do a video tutorial on these two. And then let's skip to all the way to port A, which has pin A0 all the way to pin A7. And they are ADC0, ADC1, ADC2, ADC3. ADC also simply means analog to digital conversion. And the easiest way to understand the function of this pin is by considering a potentiometer. If you know how a potentiometer works, then you also notice that it has 3 pins. If you connect the first pin to 5 volts, and the last pin to 0 volts, and then the wiper pin, which is the middle pin, will always give us an output that varies from 0 volts all the way to 5 volts. In analog format, we have 0 volts, it can be 0.1, 0.2, all the way to 5 volts. And now it is this varying voltage that we feed to one of these pins, and then the value of voltage that we get at the middle pin of our potentiometer, it's read with the microcontroller, and it's converted into digital value. If you are using 8-bit configuration for your ADC, you can use 8-bit configuration for your ADC values, or you can use 10-bit configuration. So if you're using 8-bit, for instance, at the middle pin of our potentiometer, we are getting 0 volts, varying volts from 0 to 5 volts. Let's say you vary it to 2.5 volts, which is halfway between 0 and 5 volts, and then it's read here. If you're using 8-bit configuration, that will be determined as 128, and 0 volt might give us a digital value of 0, and 5 volts will give us a digital value of 255. Similarly, if you are using a 10-bit mode configuration for ADC conversion, then its value that ranges from 0 to 1023, which would mean 1023 for 5 volts, and then 0 volt will give us 0. So 0 to 1023 are are digital values, but it will give you values 0 all the way to 1023 for 10-bit mode that will correspond to the value of voltage at the middle pin of our potentiometer. This is important because it's very important to understand this, because we have sensors that like temperature sensors that give us analog output, and this analog output is then read uh, by a microcontroller through these ADC pins. So fortunately, our Atmega32 has 8 such pins, so we can connect 8 sensors and read their output independently. And then whatever you choose to do with the data, because it is going to give you a digital value like from 0 all the way to 255 for 8-bit configuration, or from 0 all the way to 1023 for 10-bit configuration. So you can do whatever it is that you want to do with the value, that will always correspond to the value in the sensor. So that should be it for ADC conversion, and we are also going to do it because just explaining it in this way might not be helpful to some of us. So we are going to get into it, and we are going to do some projects on ADC, and you'll be able to see exactly how it works. We'll set some registers for this in our microcontroller. And then we have port C, which has pin C0 with pin C7. Not so much to talk about. Actually, I skipped these pins A, R, E, F, G, and D. We've already talked about VCC. Now, these ones are used. ARF and VCC are mostly used with when implementing ADC. To set, like ARF is used to set reference voltage. This one we can always use a capacitor to make it stable for ADC conversion. So we'll look into it. Then port C, we actually have, let me just point pin C1 and pin C0. These are always used for I2C communication. So I2C communication, like we have a number of modules and sensors and wireless devices that communicate mostly through I2C. We have the most common one, the RTC, real-time clock, which uses I2C to communicate to microcontroller. So I2C is another interesting area to consider when dealing with the field of automation. So we look into that so deeply and intensively, and we'll be able to do a project also in I2C to let us understand and get the idea of how it can be directly implemented in the field of automation. And I think that should be it. And our next video will be on our first. That it will be the first project that we'll ever do. That method, it's always simple and basic. It involves turning an LED on and off, and that will involve setting our registers in terms of output and inputs at the pins, the ports. So it's the next video we are going to do. So you'll have to stick around because these videos are arranged in such a way that if you skip one, the next will not easily work for you. So it won't be a good idea to skip any of these. And thank you for watching. And until next time, when I'll be doing our first project, uh, switching LED on and off, it's going to be really interesting. Thank you. Have a good day.